In Module 12, we'll be looking at chi-square procedures, specifically the distribution, the goodness of fit test, the independence test, and the homogeneity test. I'd like to start this lesson by talking about how the chi-square test is a statistical tool that can be used in cryptography. So in a chi-square, we measure how much observed data will deviate from expected random data. And of course, this is used in a lot of areas, but one specific example was shown here with the Enigma machine that was created by the man Alan Turing in World War II. And I have a clip on Blackboard from a movie that was made about Turing's life. Anyways, using chi-square and some cryptography, they were able to decode some secret Nazi messages. And I had the opportunity to actually see this particular machine at the Winston Churchill Museum in London. And so it's a fabulous story, and it's tied to the use of statistics, as most interesting things are. The chi-square distribution really came about to classify biological data that was skewed. And so at its highest level, it's really a way to validate how similar an observed frequency is to the expected frequency. It's used in cryptograms, as I already mentioned, but it's also used in bioinformatics. So chi-square test is used to compare the distribution of certain properties of genes, such as a mutation rate. So let's go through the basic properties of the chi-square curve. And we have already looked at this distribution and this table, so this should be a bit of a refresher. So the chi-square has property 1, the total area under a chi-square curve equals 1. A chi-square's curve starts at 0 on the horizontal line and extends indefinitely to the right, approaching but never touching the horizontal axis. So keep in mind it's to the right. A chi-square is right skewed. As the number of degrees of freedom becomes larger, the chi-square looks increasingly like a normal curve. A variable is said to have a chi-square distribution if its distribution has the shape of a special type of right skew curve, and we call that our chi-square curve. The chi-square statistic is used to test hypotheses concerning enumerated data, or what we call count data. And what I've got here is a type of table that we can use called a contingency table. And what you'll see on the contingency table is that we've got columns, and we've got rows. And this is based on real data. So I often, I always foster animals from the SPCA, and I will take in cats and kittens and bunnies. I don't take dogs just because I have so many cats, even though I also have a dog. Anyways, I've had many, many bunnies. I love them. I currently don't have any bunnies, which is, it's okay. It's a good thing. But what I've done is I collected data on how long it took for my bunnies to be potty trained. And so it's funny, people don't realize that bunnies can be potty trained, and most of the rabbits that I've had living in my home are actually free rein. They're really good. They go into their potty area, they use their box, they don't chew on things. I've only had one little guy that was sort of a chewer. So what I did here was I collected data on my male and female bunnies and how long it took for them to get potty trained. So you could see that my female bunny that I had, her name was Coco Banana. She only took 1 to 3 days, whereas my male bunnies that I've had have taken 6+ days. Now, a funny story about that is this data is based on one male bunny that actually wasn't a male. So his name was Jax. I took him in to get neutered, and I dropped him off there, and in a few hours I got a call, and they said, listen, we've got a problem with Jax. Jax has a uterus. And so Jax became Fat Jackie and was my female bunny. So this is not statistically significant, but just an example of what enumerative data looks like. Don't get too hung up on this, but I do like to show you how the data is set up. So what we'll have is we'll have observed frequencies, and they will be labeled with an O, and then we'll have expected frequencies, and they are labeled with an E. Now, we'll also have categories, and we just call them K amount of categories, and it goes to the kth number, which just means it can be any number. And then we're going to total. Now, when we're totaling the data, we're going to have row totals, and we're going to have column totals, and we will also have a separate grand total. What we're trying to do here is decide whether the observed frequencies seem to agree or disagree with the expected frequencies. So let's talk about the chi-square table. You all have copies of this table from your formula cards located on Blackboard, and so we'll go over it. So percentages and probabilities for a variable that has a chi-square distribution are equal to the area under its associated chi-square curve. Now, to perform our chi-square test, we need to know how to find the value from our table. So you're going to want to grab your table out and have it with you so you can work through this with me. Now, the chi-square table is similar to the t-table. The two outside columns of the table are labeled df, and that displays the number of degrees of freedom. And as expected, we've got a symbol, and this is like an X symbol, and this denotes the chi-square value that we have. So what we'll have is for a chi-square curve with 12 degrees of freedom, so I'm just going to circle around that 12, we would go down to the table here, and it says 12, and we want to determine the chi-square value that has an area 0.025 to its right. So with our DF of 12, and then we look across the top here, and we're going to go to our 0.025, which is over here, and we just line those guys up and we get 23.337. So make sure you try that yourself so you know how to do it. All right, here are some examples. We've already looked at this chi-square table, so I just wanted to throw a few extra examples in there. Your chi-square table on the original formula card is not as big as the one that I am showing here. You can download more of them, or I can give you another one if you need it. I think I already gave you guys an extended version. So remember to look for your DF here and match it up along the top here, whether it be the area to the right, in the left, or on the area in the right hand tail. So 19 and 0.025, if you just intersect those on here, you should get 32.852. This doesn't have as many decimal places as I have here. And for 0.952 to its right, 19, and then you intersect it with the 0.95. And for that one specifically, you're going to see that it is actually up here in this very, very top. So you're going to have to go here and intersect it down, and you'll get 10.1. So a question that you might have is, what if my DF is greater than 100 because the table doesn't go that high? And in that case, your chi-square value is going to be approximately normally distributed, and the expected values will be n. So in this case, you use the normal distribution to get an approximation, and you're not going to have to deal with that in this course. Our first chi-square procedure is called the chi-square goodness of fit test, and we can use this procedure to perform a hypothesis test about the distribution of any categorical variables or discrete quantitative variables. And so pictured here, I have Gregor Mendel, and he was the one that did invent the chi-square goodness of fit test. You may have heard of him, especially if you're in the healthcare field. He did a lot of work with genetics, and you can see he's holding peas, and so he looked at, you guys have probably done these Punnett squares before where they had the wrinkly pea and the smooth pea, and they were yellow and they were purple. That was this guy that invented it. He was also a horrible racist, so make sure you look that up. Presented here is the formula for the chi-square statistic. Now what you're going to find is that this formula is going to be the same for all of the chi-square statistics, but the way you get the information is going to change a little bit. So to obtain a chi-square subtotal, square the difference between your observed and expected frequencies and divide the result by the expected frequency. So adding the chi-square subtotals gives you the test statistic, which is approximately a chi-square distribution. And of course, what we're going to do is some practice so that we can put this into play. So you will have seen on that previous equation that we've got O and we've got E. And so O stands for our observed frequencies. And these are the numbers that are going to be given to you because they are observed. But we have to obtain our own expected frequencies. And how might we go about doing that? Now, keep in mind, this is just for the goodness of fit test. There is a different way of calculating your expected frequencies with the other tests, okay? So in the chi-square goodness of fit test, the expected frequency for each possible value is found by using this formula, which is n times p. It's very simple, but I find that people will get confused on it. So n is our sample size, and p is the relative frequency or the probability given for the value in the null hypothesis. So let's do some practice. I guess before we do practice, I should show you the full procedure. My bad. So chi-square goodness of fit test. The purpose is to perform a hypothesis test for the distribution of a variable. Our assumptions here are that all expected frequencies are 1 or greater. At most, 20% of our expected frequencies are less than 5, and it's a simple random sample. So oddly enough, in this procedure, you need to calculate your expected frequencies before you can check the assumptions. So it kind of works a little backwards. Sometimes you have to calculate the expected frequencies to see if you can actually use the test. The null and alternative hypothesis are, or null hypothesis, the variable has the specified distribution, and HA is the variable does not have the specified distribution. And this is the test statistic down here. Now, when we want to make a decision, we can employ our critical value approach and our p-value approach, just like we did in the past. But things are going to change a little bit here, particularly around your degrees of freedom. So let's check out the critical value approach first. With the critical value approach, what you're going to see is that our DF is equal to C minus 1, where C is the number of possible values for the variable, okay? Now, we're also going to have that for our p-value approach. But with the p-value approach, I don't often make you guys estimate it. I'll get you to use the critical value approach, or I'll give you the p-value, or you can use technology. So let's talk about the critical value approach a little bit more. So it's the same kind of criteria where we're going to use our chi-square table. We're going to find the critical value, and then we're going to put our test statistic here and see if it falls in our non-rejection region or our rejection region. With the p-value approach, remember we're comparing p-value that we get to our significance value that we decide. Okay, so let's do an example here. Use the chi-square goodness of fit test to decide at the specified significance level whether the distribution of the variable differs from the given distribution. So what we have is a distribution. We've got observed frequencies, and we know we're going to do our significance level of 0.05. I need you guys to know this. The observed frequencies are your observed frequencies. They're good to go. The distribution, they are not your expected values. So let's go forward and I'll show you what I mean. The first step is to translate your data into a nice table like this. You can see what I've done here is I've got the distribution as my first column, and I've got our observed frequencies here. These were just copied and pasted from the previous slide. But keep in mind that this is not your expected value. So we need to calculate the expected value. How do we do that? The expected frequency is equal to n times p. So what is our n in this situation? 500 is our n. So always sum this column here to get your 500. That's what this means. It means sum. And then to get your first expected frequency, we're going to take the distribution. This is a probability, 0.2 multiplied by 500 to give you your first expected frequency. You should try it now before I uncover this to see if you've done it right. 0.4 times 500 to get your expected frequency, and so on from there. So I'm going to uncover this one now. So what you'll see is that you get values that are sort of in the same wheelhouse as your observed values here. I'm going to give you guys a hint. It's a trick. When you add up your expected values, it has to equal the same n that you had in your observed values. So if you sum this up and it doesn't equal n, you've done something wrong. The rest of it is super duper easy. The next part is find the difference. So O minus E. So you just go 85 minus 100, 215 minus 200, and you fill in this column here. Are you going to get negative numbers? You bet your butt you are, and that's totally fine. Negative numbers are fine. Then what we do is we square the difference. So all we have to do is take negative 15 squared, 15 squared, minus 20 squared. Okay, so I'll uncover this column here, and you'll see that these are just the squares. The last part of it is taking your O minus E squared, which you did in this column right beside, and then just dividing it again by the original expected value. So it's going to be 225 divided by 100, 225 divided by 200, and so on from there. And then I'll uncover this column here, and there you go. Now, you sum this column up here, and that is your chi-squared value. Right here is your chi-squared value. Why is it your chi-square value? Let's look at the formula again. I'm going to write it out here. I'm going to try and make it as neat as possible. Your chi-squared is equal to the sum, that's a sum, of O minus E squared divided by E. That's what this is. It's the sum of O minus E divided by E. That's how you calculate your chi-square. It's actually really easy. Okay, so now let's make a decision about this chi-square. We have a DF of 3, and we have a chi-square of 14.04, and of course, this is 0.05. So if you intersect your DF of 3 and your chi-square of 0.05, you will find a critical value of 7.815. And so now you need to make a decision. And of course, it's always easiest if you draw out, a curve for you to look at. I know my curves are not the best. So let's look at our critical value here. It is 7.8-ish, and our chi-square is 14. So it's falling over here in this region, and this is our rejection region, and this is our non-rejection region. So our chi-square falls in that rejection region, and of course then we can make a decision from there if we are going to reject our HO or not. So if the value of the test statistic falls in the rejection region, we are going to reject our HO. Okay, I just want to remind you of the p-value approach here. Of course, we're going to use technology more to estimate this value, but we are going to use the table sometimes to still estimate. So how do we do that? What we're going to do is we're going to look at our table, and we're going to follow the DF line of 3. And in the body of the table, you're going to try and find the number that is closest to 14.04. And what you'll find is that the closest number is 12.838. And so that means that our p-value is less than even the closest number. So it is less than 0.005. And where did I get that 0.005? You will do your DF is along the side, right? So you go in that line, you find your number, and then you look up in the top where it will say like chi-square, and then it says 0.005. So our number is way off the table, and so in that case, we will reject. Okay, sometimes, even though the chi-square is really easy, sometimes it can be a little bit tricky, because what happens is your expected frequency is the same for all of your observed frequencies. So let's do an example of that. So we want to test a dice at alpha 0.05 and decide whether to fail to reject or reject the claim that the dice is fair. So the probability for each number is 1/6. keep that in mind. The die is rolled from a cup 60 times, and we have the following observed frequencies. So the next thing is we need to calculate our expected frequencies, which is equal to n times p. So what is n in this case? 60. But what is p? Well, p is 1/6. So let's solve this out. Okay, so first we're going to create a table we need for our chi-square, and then we'll go through all the steps of the hypothesis test. So what we want to do here is we want to write out our numbers, how many we have, and then we're going to write out our observations that we've already seen. Now, our parameter of interest is the probability at which each side of the dice will face up to see if it's fair. So our null hypothesis here is going to be the dice is fair, or the p is 1/6, so there's 1/6 that will come up. And then the alternative hypothesis is that the die is not fair, and at least one p is different from the others. Now, how do we actually go about calculating our expected frequencies? Well, it is 1/6 multiplied by 60. So 1/6 is our p and 60 is our n. And that means that you're going to get the same expected value for the whole column. And as long as this equals 60, the expected sum equals 60 as the observed sum, then we're good to go. And then you can follow through with the rest of the table and calculate your final chi-square. All right, so we can see that our chi-square down here is 2.2. Now we have to decide on our DF, and that's because it will help us to determine what approach we're going to do, critical value, p-value, and then how we are going to make a decision. So what is the DF again? It is C minus 1, where C is the number of amount of data. And so you can see here I have 1 through 6, and I do that on purpose because that automatically gives me my C, which is 6, and minus 1. So our DF in this situation is 5. So what we can do next is make a decision. So definitely grab your formula card and try to at least find your critical value approach. You want to intersect your DF with which we stated was 5 and the column 0.05. And when we do that, what we'll end up with is a critical value of 11.070. And of course, we can do the p-value approach as well. So let's make a decision here. We're going to just draw our skewed little baby, and then we've got our critical value of 11.070, and our chi-square value is 2.2. So this is in the rejection region. This is in the non-rejection region. So we are going to fail to reject our HO. All right, guys. So the other thing is checking our assumptions. And I wanted to kind of go over this a little bit because you do have to calculate your expected frequencies before you can even check all of the assumptions. So here, decide whether assumptions 1 and 2 for using the chi-square are satisfied. So again, assumption 1 is that all expected frequencies are 1 or greater. And if we look at the expected frequencies, we just from a visual analysis, we can see that they're all 1 or greater. The second one is that at most 20% of the expected frequencies are less than 5. So if we look at this, how many of them are actually less than 5? Only 1 is less than 5, and that's 1 out of how many of them? We have 6 of them, right? Or no, we have 5 of them here. 1, 2, 3, 4, 5. So we only have 1 out of 5, and that is 20%. So we meet that one because at most 20% of the expected frequencies are less than 5, and that it's a simple random sample. So make sure you're always checking for those things. So remember, it is that all expected frequencies are 1 or more, and that we've got at most 20% of our expected frequencies are less than 5. We only have 1 that's less than 5, and that's 1 out of the 5 that we have there, which equals 20%, so we're good to go. Okay, we're going to move on to the next two types of chi-squares, and these are inferences concerning contingency tables. Data from one variable of a population are called univariate data. And now we want to look at how to simultaneously group data from two variables into a frequency distribution. So data from two variables of a population are called bivariate data, and a frequency distribution for bivariate data is a contingency table. It will also be called something like a two-way table, a crosstab, or cross-tabulation table. And that brings me to talking about association between variables. We need to discuss that concept. So, roughly speaking, two variables of a population are associated if knowing the value of one variable will impart some sort of information about the valuable or the value of the other variable. So we say that two variables of a population are associated, or that an association exists between these two variables if the conditional distributions of one variable given the other are not identical. One of the most commonly used procedures for making decisions is the chi-square independence test. And I'm going to introduce and kind of explain the reasoning behind the chi-square independence test. I want to start though by talking about the expected frequencies. Previously to this, in the goodness of fit test, we would find our expected frequencies by taking n multiplying by p, but it changes now. So now if we want to find our expected frequencies, what we have to do is we have to take the row total, multiply it by the column total, and divide it by n, which is the sample size. But the actual formula for the chi-square independence test is the exact same as it was for the goodness of fit. But what you'll see now is that the degrees of freedom again change. So the chi-square independence test statistic is equal to the sum of the observed minus the expected frequencies squared divided by the expected frequencies. Adding the chi-square subtotals gives the chi-square statistic, which has the approximate chi-square distribution. And remember, our degrees of freedom now are going to be the rows minus 1 multiplied by the columns minus 1. So this is on your formula card, and I think that people forget that the formula card is such a wealth of information for you, but feel free to add more information onto your formula card should you want it, because again, the goodness of fit, the chi-square independence, and the homogeneity test all have the same actual calculation, but how you calculate your expected frequencies, how you calculate your DF, and your hypotheses will change. Let's look at the procedure for the chi-square independence test. The purpose is to perform a hypothesis test to decide whether two variables are associated. Our assumptions are that all expected frequencies are 1 or greater. At most, 20% of the expected frequencies are less than 5, and it's a simple random sample. So that's all the same as the goodness of fit. But check out your null and alternative hypotheses. These change. The null hypothesis is asking that the two variables are not associated, while the alternative is stating that they are associated, and then the rest of the steps are generally the same. And you know what else is relatively the same? Your critical value approach and your p-value approach. The only thing that changes here is the way that you calculate your degrees of freedom. Remember, for this one, the degrees of freedom is the row minus 1 multiplied by the columns minus 1. And when I say the row minus 1, I mean the amount of rows. Like, are there 4 rows? And what you'll find in chi-square is that often you have really small DF. So let's do an example. In this example here, there was a group of 300 Medicine Hat College students that identified their dietary preference as vegan or vegetarian or not. And then they were asked their favorite subject area or types of courses they like taking at MHC. And what we were able to form was a contingency table that shows the frequencies found for these categories. So the question is, does this sample present sufficient evidence to reject the null hypothesis that preference of subject area is independent of the dietary preference of an MHC college student. And we're going to do the hypothesis test, and we're going to complete it at the 0.05 level. Now, a couple things I want you guys to note right away is that we've got totals. Okay, so add 37 and 35, it's 72. Business is 41 plus 72 is totals, right? And then we also have a total here. So 37 plus 41 plus 44 is 122. This number here, the 300, is your grand total. That is your N. So let's review the procedure. The parameter of interest are the two variables associated. Our null hypothesis is preference for a subject area is independent of dietary preference of an MHC college student, whereas alternative hypothesis is the subject area preference is not independent of the dietary preference of the MHC college student. Okay, so as with the independence test or the homogeneity test, the steps for carrying out is the same. But how are we going to get our expected frequencies? So what we do for expected frequencies is your row total times your column total over the grand total. Don't get confused about these subscripts. They're just indicating that it can be any number. Then we've got our DF is R minus 1 times C minus 1. And then we've got our actual chi-square statistic. So we can actually make a nice clean table like we did with the goodness of fit, but I'll show you guys another way that you can do it. So let's calculate our expected values. What you'll see here is in science, I've got 72, which is our row total, multiplied by 122, which is our column total, divided by 300, which is our grand total, and we get 29.28. The original number was 37, so it's kind of in that wheelhouse. It looks good. Try it again for yourself now. How would you have gotten this one here, this 42.72? Well, we've got our row total, which is 178, and then you will multiply by your column total, which is 72, and then you divide it by 300, and you have to do it for every single one of them. So what I end up doing is I always put the expected and the observed in the same kind of column so that I can visualize it. Now, once I have all of my expected and my observed values, what I'll do is I'll actually just do the old school sort of calculation where I get the observed value minus the expected value squared over the expected value, and then I add them for every single one of them to get the sum. So you can see here that I've got my observed value, my expected value divided by the expected value again. And then you add those all together and your chi-square value that you get is 4.577. Now it's really easy to watch me do this or to have all the answers on here, but it's really essential that you try it for yourself so that you know how to do it as well. And then we just have to make a decision. And of course, we can use our critical value approach, or we can use our p-value approach for this, where the DF is R minus 1 times C minus 1. Okay, so let's do this. Let's make some decisions here. We'll start with our p-value approach to make a decision about the chi-square of 4.604. So we have a DF of 2. And where did that come from? We had rows minus 1 times columns minus 1. And if you go back and look at it, we had two options. You were either a vegetarian or you were not a vegetarian. And we had a couple options over here where it was like, I think we had 3 options where it was science, social, whatever it was, minus 1. That's how you get your DF. So in this case, our DF is going to be 2. So to find our p-value, what we'll do is we'll take our 2 and we'll go across the table and look in there for the number that is closest to 4.604. And it looks like it falls in between these guys right here. And so then we'll go up from there, and then we can see that our p-value is going to fall between 0.10. So it'll be greater than 0.10, but it will be less than 0.25. 5. So this is not smaller than our alpha of 0.05, so we do not reject our HO in this situation. Now in that last slide, I didn't show you how to get the critical value, but I did put the critical value on there, and it is like 5.99, something like that. So make sure using your DF and your alpha, you can find that critical value as well. Okay, we're moving on to our final chi-square test. This is the test of homogeneity. The purpose of this test is to compare the distributions of a variable of 2 or more populations. As a special case, it can be used to decide whether a difference exists among 2 or more population proportions as well. So let's go through the steps for this one. Okay, so the actual testing for the independence and the homogeneity with contingency tables is the same, but there's a big conceptual difference here that will be based upon the hypothesis. And in the test of the homogeneity, we're actually testing the hypothesis the distribution of the proportions within the rows is the same for all the rows, or you can think of it like the distributions of proportions in row 1 is the same as that in row 2, is the same as that in row 3, and so on, with the alternative being the distribution of proportions within rows is not the same for all rows. And so when you think of homogeneity, I think that a really good way to conceptualize it is to think about survey data if you were getting information back. And so I've done a little bit of a comparator here. The context and the assumptions differ for the independence and the homogeneity test. So the purpose is different as well. So with the independence, we're trying to see if they are associated. With the homogeneity, we want to perform a hypothesis test to compare the distributions of a variable of 2 or more populations. Now the assumptions are almost the same, except for in the homogeneity test, one of the assumptions is that we have independent samples. And so the observed frequencies for the homogeneity test will be arranged in a contingency table, and the expected frequencies are computed in the same way, where you take the row total multiplied by the column total and take that over the grand total. The test statistic is also the same. So to obtain the chi-square subtotal, square the difference between an observed and expected frequency and divide the result by the expected frequency. So the degrees of freedom is also calculated in the same manner. And so what's really different here is that one assumption and the hypothesis. Okay, I know I'm beating a dead horse, so this is the last time. But what is the difference between the independence and the homogeneity tests? Well, aside from their purpose, and assumptions that we've talked about, it is really the hypothesis part, and it is essentially you know the difference between these tests and when you should use them. So again, homogeneity, are the populations the same? And then with the independence, are they associated? And here is the procedure for the chi-square homogeneity test. The purpose is to perform a hypothesis test to compare the distributions of a variable of 2 or more populations. The assumptions are that all expected frequencies are 1 or greater. At most, 20% of the expected frequencies are less than 5. It's simple random samples and they are independent. The null and alternative hypothesis here are that the populations are homogeneous with respect to the variable, or they're the same, or the populations are not homogeneous with respect to the variable. And then, of course, the calculation, the critical value approach, and the p-value approach are all the same. Okay, so let's do an example of this. In this example here, we had 500 employees at different stores, Banana Republic, Gap, and Old Navy, because they're all affiliated together. And so they were asked their opinion on wearing masks after COVID-19 restrictions. And so you can see in the contingency table, we've got Banana Republic, Gap, Old Navy. Okay, so these are our rows. And of course, R minus 1, 3 minus 1 is 2. And they were either in favor or they were opposed to it. And these are our columns, and we only have 2 of them. So that will be 2 minus 1 is 1. Okay, so the parameter of interest here is the proportion of the employees who wanted or opposed having masks after restrictions. And the hypothesis here is generally that all the employees are homogeneous with respect. They all agree with this, or they are not homogeneous. Most of them don't agree with it. So, of course, we've got our expected value calculation that we have to do here. And remember, that calculation is going to be the row total, so 200, times the column total, 254, divided by the grand total, which is our n of 500. And we can also go through the assumptions. Of course, you have to calculate your expected values before you can do those assumptions. Okay, so now that we have all of our expected values and our observed values, we can calculate our chi-square here. And what we'll do is take our observed value, so like 143 minus 101.6 squared over the expected value, add them all together, sum it up, and then you get 91.72. And this is the value of chi-square for us. And now we just need to make a decision. Let's make a decision using our critical value approach. So look in your table for your DF of 2, and we're going to intersect that with our 0.05 that we have decided on. And when we do that, I'm just looking for it here in the table. There it is. And when we intersect those, we get 5.99. So that's our critical value. And of course, our value of our chi-square is 91.72, which falls over here. And remember that this is our rejection region. And if it fell on the other side of that 5.99, it would be our non-rejection region. So in this case, we are going to reject HO. And we can say that the people do not all have same proportions favoring favoring the proposal to wear the masks after restrictions. Now, if we were going to do our p-value approach, but we weren't going to be using any sort of technology to do that, keep in mind what we're going to do is go in row 2 for our DF, and we're going to try and find the number that is closest to our 91.72, and you can see that the closest one is 10.6. And that means that it's way off the table here. And so that you can see that P in this case is less than 0.05. Okay, so hopefully that works out for you guys. And you enjoyed this. I think that the chi-square is actually really fun to do.